Section 4.6, the Forces of Friction. Our learning objectives in this chapter are to 1. Explain the physical origins of friction forces, 2. Apply the concept of the kinetic friction force, 3. Apply the concept of the static friction force, and 4. Apply the system approach to multiple body problems. An object moving on a surface or through a viscous medium, such as air or water, encounters resistance as it interacts with its surroundings. This resistance is called friction. Friction can be a good thing in a lot of situations. Friction makes it possible to grip and hold things, drive a car, walk, and run. Even standing in one spot would be impossible without friction, as the slightest shift would instantly cause you to slip and fall. Imagine you've filled a plastic trash can with yard clippings and want to drag the can across the surface of a concrete patio. If you apply an external force F, as shown in figure 4.21a, the can remains stationary if F is small. The force F sub S counteracts the force of friction, and it increases to counteract the force. As you increase this force, the counteracting static friction force will exactly balance it until you reach some threshold. And then once you get over a certain threshold, then the can will start to move and the force of kinetic friction will take over. Usually this force of kinetic friction is less than the maximum force of static friction. This chart shows how, as you increase the force on the can, at a certain point it will reach, static friction will reach a max, and then the amount of friction will go down and you'll have a force of kinetic friction while the can is moving. I'm going to introduce these two ratios. Mu sub s, that's it's mu. Mu sub s is the coefficient of static friction, which is the maximum static frictional force divided by the normal force. So if I have a normal force going down like that, and the frictional force, we'll have frictional force max going this way, or the maximum static friction going that way, and we have just reached that point so that the force is just equal to the force, the maximum static force. Then you will find that the ratio of this force divided by this force is mu sub s. And okay, that's when the thing is stopped. But when we have it moving, and this thing is moving right along, we'll have the force in the kinetic, or the kinetic frictional force pushing that way with whatever force we have pushing forward. We may not even have a force pushing forward. We could have that covered up and the object would be slowing down. And then whatever normal force is happening from here. And the normal force can be a combination of, it's generally equal to the gravitational force. The normal force is going up, the gravitational force is going down, but sometimes you can apply pressure to that. Okay, that's my attempt to draw a hand, but the idea is if you push down extra on there, then if you push down with your finger, you would have the force of your finger pushing down, the force of gravity pushing down, and the normal force pushing up on the object, and the total of the force, the normal force, since it's not accelerating up or down, the normal force uh, is equal to the finger force plus the gravitational force, or the magnitudes are equal anyway. They're equal and opposite. Anyway, look at the difference between these two things. This says the static friction is less than or equal to mu sub s times the normal force. This one says the force of kinetic friction is equal to mu sub k times n. So to put those equations into a little table, the force of static friction is going to be less than or equal to mu sub s times n, so long as the object is not moving. Also, the static frictional force is equal and opposite to the parallel force. This is the force parallel to the surface. Um, and here, when the object is moving, there will be a kinetic frictional force that is equal to mu sub k times the normal force. I thought I would make a distinction here. We're talking about an object that is moving along the surface of the ground. Um, there is also something called the drag equation, which is for an object that is flying through the air, and it is actually proportional. There, the u squared, or the v squared here, is the velocity of the object, where rho is just the density of the fluid, c sub d is the drag coefficient, and a is the cross-sectional area of the object. But all that is to say that instead of being proportional to the normal force, um, that the friction of wind is proportional to the velocity of the object squared. Now, we're not going to look at this equation in this chapter. I just wanted to put it there as a kind of like a comparison to some other kinds of friction that actually exist but aren't mentioned in this chapter. Here is a table of coefficients of friction, and it says down here all values are approximate. And for this, the highest coefficient of friction listed in the mu sub s area is glass on glass, and it is apparently very difficult for glass to slide on glass. Oh, wait, here's an even higher one. Rubber on concrete is 1.0. I think it's interesting that all of these have like a 1 limit, because well, here's the thing. We'll be finding later on that one way of calculating the mu sub s is finding out the rise over the run when this thing starts to slip. And there's no theoretical reason that it shouldn't be possible for something to not slide until, say, 60 degrees or 75 degrees. And but I mean, looks a little unlikely. But if this was made of some kind of sticky substance or something like that, then it would be able to lift and have an actual coefficient of friction that was more than 1. The mu sub k values are generally considerably lower than the mu sub s, because once you do start slipping, it usually, if you've started slipping from here, once you do start slipping, you start accelerating. Quick quizzes. Number 4.7. If you press a book flat against a vertical wall with your hand, in what direction is the friction force exerted by the wall on the book? So here's your book, here's your hand, here's your wall. You got force on the book, its weight acting downwards, and you've got the friction between your hand going up, and you've got the friction of the wall pulling up. And then you've also got the force of your hand going this way, and the force of the wall going this way. So this is the normal force, and friction force, and then the weight. Quick quiz 4.8. A crate is sitting in the center of a flatbed truck. As the truck accelerates to the east, the crate moves with it, not sliding on the bed of the truck. In what direction is the frictional force exerted by the bed of the truck on the crate? Okay, so the truck is accelerating to the east. The crate is also accelerating to the east because it's frictional force, or the static friction. And so that means, since there's no other force acting to the left or right, or I'm sorry, that's not a force, that's an acceleration. So acceleration equals the sum of forces to the left and right divided by its mass. So the force of friction, force of static friction, is also to the right, or B to the east. Quick quiz 4.9. Suppose your friend is sitting in a sled, look at that, and asks you to move her across a flat horizontal field. You have a choice of A, pushing her from behind by applying a force downward on her shoulders at 30 degrees below the horizontal, or B, attaching a rope to the front of the sled and pulling with a force at 30 degrees above the horizontal. Which option would be easier and why? Okay, when he's pushing down on the crate, there is two forces acting up in the up-down direction on the sled. The mass times gravity is acting downward, and the force times sine 30 is acting downwards. Those are the forces that are acting downward on the sled. The normal force is equal and opposite, which is mg plus force times sine 30. When the person is pulling upward on the sled, there are two forces acting in the y direction, mass times gravity acting downward, and force times sine 30 acting upwards. So this is the force acting downward on the sled. So the force acting upward is the same, the normal force, and so the force of kinetic friction is going to be mu sub k times n, which will be mu sub k times mg plus or minus f sine 30, depending on whether you're pulling upward or pulling downward or upward. So the minus f sine 30 is going to be easier. So this will be answer B, attaching a rope to the front of the sled and pulling with a force of 30 degrees above the horizontal.